Dr. Venktesh Viswanathan. He will be speaking on robust and efficient frontier pipelines for complex knowledge-intensive tasks in the era of LLMs. Dr. Viswanathan is a postdoctoral researcher in Web Information Systems Group in Department of EEMCS at TU Delft, working with Dr. Abhishek Anand. He completed his PhD at IIIT Delhi, India, complex knowledge-intensive task in the era of LLMs. Dr. Viswanathan is a postdoctoral researcher in Web Information Systems Group in Department of EEMCS at TU Delft. He completed his PhD at IIIT Delhi, India, and is also the recipient of the prestigious PMIT Award. His thesis was titled Learning Content in the Era of LLMs, where he worked is a postdoctoral researcher in Web Information Systems Group online learning development of EEMC. Also worked on improving knowledge. He completed his PhD at IIT India and is also the recipient of PhD at PMIT Award in knowledge learning content in the era of LLMs, like complex fact checking and complex question answering for applications that have direct social impact. We request the audience to keep your microphone silent for the duration of the talk, except when asking questions. And for asking questions, please raise your hand, unmute yourself, and ask directly or type them in the chat box, and we will relay your questions. Thank you. Over to you, Mr. Dr. Vishwanath.
Yeah. So do I start? Hello. Am I audible? Hello. Hello.
Yes, you are audible.
Yeah. Okay. So can I start?
Yes.
Yeah. Thank you for the introduction, and I would like to start off by thanking the organizers for this invitation to deliver this talk. And I think you already heard about the introduction, so I'll just start off on my talk. So today I'm going to sort of present my research works on this title, like broadly encapsulated by this title of building robust and efficient frontier pipelines for complex knowledge intensive tasks in the era of large language models. So the title is quite involved, but bear with me and I'll break it down in the duration of this talk. So first, I would like to break down on what I mean by knowledge intensive language tasks. So as you can see here, I have this two axes of efficiency and effectiveness, and I'm sort of going to introduce some tasks which sort of require both of these parameters, right? So knowledge intensive language tasks can be defined as those natural language processing tasks which sort of require reasoning over multiple knowledge bases, right? So you have really simple tasks like factoid question answering or those kind of tasks which require like simple factoid answers, just look up. Whereas knowledge intensive tasks require you to reason over multiple knowledge bases, right? For example, fact checking. So if you see how fact checking is done manually, a manual fact checker usually like sort of takes a claim made by, some politician or some expert and sort of breaks it down and searches the web, searches knowledge archives, gets relevant information and sort of makes his own inferences, right? To sort of see whether a particular evidence is supporting the claim or refuting the claim. So he tries to get diverse perspectives, reasons about this, and gives his verdict and reasoning, right? So in a way, it's also subjective. But if you can see the process here, it's quite intensive, right? Even for a human being. And if you sort of want to automate this, your systems sort of consist of complex pipelines, right? Which should distill the information from large knowledge bases and sort of get only the relevant facts relevant to the current query and then reason over this evidences and sort of give a reasoning and a final output, right? So if you see towards the right extreme of this axis, you have applications like fact checking articles, right? Automated fact checking. And you also have financial auditing, right? Like assume you are sort of like a financial research intern like in a big consultancy, and you're sort of asked to audit a certain company, right? So you have to go through the financial records, you have to go through the bylaws, and you sort of have to make inferences and as to whether there is a profit or a deficit or what kind of departments need a restructure and so on, right? So this also requires complex numerical reasoning and reasoning over multiple sources, and also about like factual article generation, right? For example, like let's say you want to automate generation of some factual articles on Wikipedia pages, right? To update Wikipedia pages to maintain them. So this also needs very high precision, right? You can't just have wrong information in any of these pages. So these tasks sort of require high precision, so you need high effectiveness, no matter what the pipeline you're employing. And on the left extreme of this axis, you have efficiency, right? And as you can see, the applications are like conversational AI, which is like at all-time popularity, right, in the recent ages, and also web search, which any of us do, right? Like which is like one of the most common applications everyone interacts with, and also live fact checking, right? And live fact checking is very important in the current age where, podcasts are becoming really popular, or even in context of political debates, right? Or where experts also engage in this podcast and non-experts also do. So if someone is popular is making a statement, it could have good or bad consequences based on the factuality of this information, right? So having live fact checking sort of helps people peruse the corresponding sources cited and make informed decisions for themselves, right? And for all these applications, low latency is a non-negotiable, right? You can't be like, okay, I'll do really good reasoning, but then you'd have to wait for a few minutes before you get the response. That is not going to work out, right? So my research involves reconciling these two extremes of the axis. How do we ensure reasonable effectiveness while making sure it's really efficient, right? And of course, I'm going to discuss the solutions, but the recipe for solutions involve optimizing the information retrieval component of the pipeline and the reasoning component of the pipeline, right? So if you see the normal solution pipelines for this broad range of tasks, there is a single solution recipe, right? Where you extract information from some source and you look to information retrieval techniques for doing the same. And then once you have the relevant information, you give it to a task specific model, which is going to do the reasoning, right? So the indexing and pre-computing some information for the retrieval part is one recipe. And basically scaling test time reasoning is another recipe, right? And I'll further break down on what I mean by this terminologies. But before that, I would like to sort of introduce the solution paradigms, right? So now in 2025, like LLMs have really picked up a lot, right? And almost all forms of research areas involve interacting with LLMs or trying to figure out what they really do, right? And one popular term which is coming about is agentic AI, right? Though it's like a fancy term for something which we have already been doing in NLP and IR for a long time, where we build this compound systems which interact with each other. They also sort of interact with the environment, get feedback, and these are commonly called agents, right? And the only difference is that these systems which we used to talk with each other in form of latent representations, right? Which is not really interpretable to us, the end user or the any human involved in building the systems. But now with large language models, you have this advantage of natural language interfaces, right? So a LLM could sort of use natural language to describe what information it wants. And this is sort of interpretable, though there is no way to say if that's exactly how it's doing the reasoning, right? But it's a bit better than interacting with latent representations. So the LLM can sort of do planning. Some works have shown this, that they could sort of break down a task and ask for more information, or draw inferences and give the prediction. And they could also use other deterministic tools, right? Like calculators or code interpreters based on the task. For example, if you're looking for a LLM to do some coding, it could sort of use a code interpreter to see if the code runs. And it could also use web search to sort of get more information, or it could also use external memory, which probably has some domain specific knowledge and so on, right? So now with this paradigm, I think one common belief is that, okay, LLMs, once we have a big enough LLM which sort of encodes all the knowledge, it can solve all the tasks. But I think this is also a common misconception. We don't have a LLM as such yet. And there are some common problems, right? And the most common among them being hallucination, which I think this terminology a lot of people would have heard. So what exactly do we mean by hallucination? It's sort of like LLM makes plausible information, which is not factual, right? Which is not correct. And one example, as you can see here on screen, is assume there is a medical chatbot, right? Chatbot for the healthcare domain. And a patient comes to this chatbot and sort of asks information, right, as to what causes Noonan syndrome. So the LLM gives a very technical answer, right? It highlights that it's caused by a certain gene, and it's also hyperlinked, which means it's giving some citations here, right? And then it also explains how this gene mutation can cause this particular syndrome. So to a non-medical person, this answer looks very plausible, right? It's highly technical. And probably if you just Google this gene, you'll see that maybe that gene exists and so on. So this appears to be a highly technical answer and someone may even trust it, right? And there also appears to be some citations. But if you actually see, this answer is completely wrong. This gene has nothing to do with this syndrome. And the citations are also sort of like made up, right? So some of these citations do exist, but has no relation to this particular gene, or some citations are entirely made up. So unless someone does in-depth research on the citations, there is no way for them to know that this is not a correct answer. So imagine if a patient makes self-diagnosis based on this response, or let's say a new medical resident uses this to prepare a report, which might be perused by someone else, right? And it could have catastrophic consequences. Or imagine a lawyer, a new lawyer sort of making arguments based on LLM outputs, right? And it could also have disastrous consequences because there is no provenance, right? There is no way to know if the answer is grounded on domain knowledge and if it's pointing to the correct sources, right? If you just ask a LLM out of the box. And these are not just imaginary made up examples, right? There are many real world consequences we are already seeing. The first consequence you can trace us back to 2022, right? Like where Meta AI released this really large language model called Galactica, which they claim can write entire research papers from scratch. And of course, the community, the open source community started testing it and they figured out that it made up scientific knowledge and it also made up citations. And everyone sort of protested, saying that it could lead to really bad papers, right? And the conferences would also be overwhelmed, and people who are interacting with the field for the first time may assume some of this knowledge to be factual and true, and it's actually not. And this model had to be taken down, right? So Meta AI had to retract open sourcing this model. And then there are also other problems in other domains, like this particular lawyer example, which I gave, it happened in real life, where the LLM made up citations, right? And case precedences, and the judge fined the corresponding lawyers. And also some airlines which tried to automate customer support, they released this chatbot, which made up its own airline policies, right? Policies which do not exist in Air Canada, and they had to pay a lot of money in damages. So now one of the overarching questions after we saw all these examples and these problems is how do we mitigate this hallucination and establish provenance, right? So there is no, and before we go any further, like there is no definitive solution, right? Something that completely solves hallucination. Of course, that would be the holy grail. There is no holy grail, but there are some approaches which have shown to mitigate hallucination, right? With some guarantees. So one of the solutions that could first come to mind is why can't we just ask the LLM to explain itself, right? Okay, you're just asking LLM for an answer, it gives you an answer. But maybe if you ask for reasoning process, right, as to how it is arriving at the answer, maybe it might help you solve some issues, right? But this is not the case because again, there are knowledge gaps. For example, if the LLM pre-training data has not seen some records, or if the LLM is not able to recall some information, it could just say, I don't know how to reason about this, right? It could take a shortcut and give you an answer, but when you ask it to reason, it could just, in this particular example on the right, you see it's a compositional reasoning question, right? So I'm basically asking, what is the mouth of the river, which serves as the mouth of the bumping river, right? So you first have to find which is the mouth of the bumping river, and then you have to get its name, and then you have to find what is the mouth of that particular river, right? And the model is not able to reason about this. And another example, as you see on the left, is a numerical reasoning question, right? So there's a math word problem, and I just asked the LLM, hey, give me a solution for this problem, but describe how would you go about solving it, right? And It gives a very plausible reasoning, but this reasoning is not faithful to its final answer. So the final answer is 0. But if you sort of see the reasoning, it nowhere leads to that particular answer, right? So here's what we call like faithfulness of the LLM. This is unfaithful reasoning because your reasoning is not faithful to your final answer, right? This could happen when the model takes a shortcut and guesses an answer, or it sort of makes up a certain reasoning path, right? It could happen in either of these cases. And there is no way to sort of tell what is happening in this particular scenario. But one solution that's really stood the test of time is retrieval augmented generation, right? So this terminology also is very popular. It's been popularized in the recent 2 years, but if you sort of trace it back, there is this 2020 paper by Patrick Lewis, which sort of presents this idea of retrieval augmented generation, a unifying framework for different knowledge intensive tasks. But it goes as back to like early 2015 or 2014, right? Where retrieval has been used to solve question answering. And the information, a lot of inspiration has been drawn from the information retrieval field, right? Where basically you have this 3-step process, right? So your end task could be anything, right? It could be fact verification, it could be question answering, or any kind of knowledge intensive task. So what you have first is you need to get relevant knowledge, right, to solve a particular query for either of these tasks. So now you have a huge knowledge base, assume the entirety of the web or Wikipedia or whatever, right? And you have billions or millions of documents. And now first you need to like filter out information and only get documents relevant for this particular query, right? Which could be like a few hundred documents or much less than that. So you sort of do retrieval and ranking, and I'll elaborate more on the differences between both of this, but you have this 2 stage where you first retrieve some information and you reduce billions to maybe a few millions or hundreds, and then you further filter it down through ranking to a few documents. And now you send these documents to a task specific model, right? So these models could be fine-tuned to perform the reasoning for the end task. For example, in fact verification, you could have natural language inference models, right? Which sort of classify whether a claim is true or not. Or you could sort of have like question answering models, which is going to pick a span in the given evidence. If it's like factoid question answering, it could just point to a span saying this is the answer, right? So you used to have this task specific models, which are fine tuned for the specific tasks. But now with LLMs, this paradigm has changed, right? So you no more need to train task-specific reasoning models. You sort of have this LLM, which is pre-trained on a wide range of tasks and also on diverse corpora. And you just need to give it some instructions to do reasoning corresponding to the end task, right? And this is found to work well to some extent. So if you just give the relevant knowledge, probably the LLM is able to solve it better, right? And you need not train any task-specific model. So this is the whole paradigm of retrieval augmented generation. So first I'm going to cover about the retrieval and ranking part here. So as you can see, there are like 3 different components, right? Retrieval, ranking, and you have the generative model, the reasoning model, right? And reasoning is a subjective term, but I'm sort of taking the definition from literature for this case, because there is debate as to whether LLMs are really doing reasoning, but for the purposes of consistency with literature, I'm sort of going with reasoning here. So first, I'm going to present this telescoping view of retrieve re-rank pipelines, right? You can think of them as a telescope. So you have this millions of documents, right? You have a huge corpus. And now first you want to quickly filter them, right? Remember, you want the latency to be low. So you can't do a pairwise check whether each of these documents is relevant to the query, right? And you can't sort of have a very elaborate process for this because it will be extremely slow. So you sort of need to quickly skim through them and get the most relevant documents. So you sort of use lexical or semantic retrieval pipelines, right, which are fast, but are really noisy estimators of relevance, right? And now you bring them down to thousands for the query you want to answer. And now you want more precise estimators of relevance, right, to further filter them out and get only the really relevant documents that will help you answer the query. So that's when you bring in re-ranking, which is like more precise estimators of relevance, right? And usually all the cross-encoder models are used as re-rankers, and now you also have LLM re-rankers, but it could be any model, right? And now, if you see in terms of like efficiency, the retrieval takes only like 5% of the time, right? It's really fast. But the re-ranker takes 95% of the time, right? Because it's slow, but it's going to give you precise estimates. That's why you sort of re-rank only few hundred or few thousand documents, right? You don't re-rank millions of documents. So the question here is, how do we capture most of the relevant documents while still reducing this time, right? The re-rankers are still expensive. So this also forms like one of the pillars of my research goals. And efficiency is one issue, even with the current retrieve re-rank pipelines, but another issue is basically effectiveness, right? In terms of, I'd like to call this the bounded recall problem, right? So as you can see here, you go from millions of documents to few thousand documents, right, through your first stage retrieval. And basically your ranker is only going to see this few thousand documents, right? So whatever you're capturing in this first stage retrieval, the ranker is limited by those documents. And if through this noisy estimators of relevance, if you're not capturing all the relevant documents, then they're lost forever, right? And this is what you can see in this plot in the right of the slide here. On the x-axis, I have retrieval scores, and on the y-axis, I have re-ranking scores, right? So if you sort of see to the right of this dotted line, the green region, you have documents with really high retrieval scores and also potentially high ranking scores, right? And you're capturing some of these relevant documents. And this is what your traditional pipelines do, right? But they're missing out on so many relevant documents which have low retrieval scores, right? And maybe they might have ranking scores, but there is no way to know because you're not scheduling them, right? In your first stage retrieval, you're not capturing them. So these documents are lost forever. So what we would really like is to capture also some of these potentially low retrieval score documents, which might be potentially a relevant document, right? And what kind of signal might indicate is some of these documents with low retrieval scores could be sort of close to documents with high retrieval or high ranking scores, right? And if you can sort of capture the signal, maybe we can potentially also explore these documents, right? And we'll see more on this in detail later, but it's sort of important to keep this view in your mind, right? Like what's the limitation of telescoping systems? So this bounded recall problem also affects reasoning, right? Because if you don't capture relevant documents, your LLM is going to falter. So now I would like to first pose two questions to which I'll be presenting the solution. How do we capture more of these relevant documents, right? Moving beyond this recall boundedness issue. And how do we ensure that these documents are ranked really high, right? Because for RAG, this problem is further exacerbated, right? Because your LLM context length is limited. You can probably fit in only 5 or 10 documents, not hundreds of documents. So you want to make sure that whatever documents are in top 5 or top 10 after ranking, they are really relevant, right? As many relevant documents as possible. You have to ensure that you're capturing in this limited context. So these are the first two questions I'm going to try and solve. But before that, I'd also like to present the broad two categories of my research questions, which I address in my research vision, right? One is the retrieval gap, which is something I just presented, right? The recall boundedness issue, and the other is the reasoning gap, right? So retrieval gap, as you already know, is this recall boundedness issue, and the reasoning gap is the fundamental limitation of LLMs. When even given the right context, they may not be able to solve certain kind of questions, right? And to sort of illustrate this, you have these two plots on two popular compositional reasoning benchmarks, right? Similar to the bumping river question, which I just presented. When you sort of present this to an expert or to a human, you see this ideal performance, which is the green bar on the plot, which is like really high, right? Of course, it's not 100%, but it's really high. And if you can see the current state of the art systems in reasoning, all the large language models, they are like really low in performance of multiple orders of magnitude. And you can see that this is also a direct consequence of low retrieval performance, right? As you can see in the bar plot on the left. So my research is going to see how we can sort of bring this blue bar up, right? And to sort of solve the first two questions I just proposed here, which is about, closing this recall gap, this recall boundedness issue, and to sort of also bridge the reasoning gap to some extent, right? And to make sure we capture the most of the relevant documents. I'm sort of going to present this work, which has been recently published in NACL, called Sonar, a system which we proposed. And of course, it also has a long, boring title, Semantic Uncertainty-Based Neighborhood Aware Retrieval. But the gist is just this, right? Like, our goal is to capture more documents beyond the first stage retrieval, right? Going beyond the recall gap. And the second part is to make sure that these documents are useful for reasoning, right? By getting some form of feedback from LLM in the form of LLM uncertainty, right? So I'm going to elaborate on this further, but this is like the recipe for the solution. So on the top of this diagram, you can see the classical QA system, right? So once you get a complex question, like the bumping river example, you sort of decompose this question, right, into smaller sub-questions. And for each of the sub-questions, you do retrieval, and then you do ranking, and then you do LLM reasoning, right? And you keep doing this till you arrive at the final answer. This is a classical pipeline, but as you can see, there is the recall boundedness issue from the first stage retrieval, right? So we sort of took a slightly different approach. First, what we did was offline, we took this huge corpus, right, which has millions of documents or billions of documents, and we built a corpus graph. So what the corpus graph is, it's very simple. For each document, I select a neighborhood of 100 documents, right? And these neighborhood is selected based on which documents are closer to the source document, based either on lexical similarity or semantic similarity, right, between the document representations. And you do this for each document in the corpus, right? You take top 16 or top 100, and you form this corpus graph. And this is a one-time process, right? It's a bit of a costly process, but it's one time and it's done offline. And you just pre-compute this and index this. And at inference time, once you get a question, what you do is like, you again sort of decompose it into sub-questions, right? And for each sub-question, you first do first stage retrieval using BM25 or any dense retrieval, right? Fast but less precise estimators of relevance, you get maybe top 100 documents. And now instead of just re-ranking this 100 documents, you first take the first 16 documents, right, out of this 100 retrieved documents, and then you re-rank them, right? You re-rank in batches, right? So assuming a batch size of 16, you re-rank the 16 documents, and then you look up their neighbors from the corpus graph, right? And you get the top neighbors, right, based on the affinity to the source document, right? You have this document scores, which you have captured. Based on this affinity, you take top 16 neighbors from here and add it to a separate pool, which I would like to call here as neighborhood pool, right? So now you have two lists, right? You have the initial retrieve list and you have this neighborhood pool. Now, instead of ranking the next 16 documents in your initial retrieve list, you go to the neighborhood pool, right? And basically the idea here is that if you remember, I talked about finding the friends of highly relevant guys, right? Documents which have low retrieval scores, but maybe if they are a friend of a highly relevant guy, you might want to consider them, right? So by sort of also ranking documents from the neighboring pool, you're ensuring this happens. And till you reach the budget of, let's say, re-ranking 100 documents, you sort of alternate between these two lists, right? So first you did the first stage retrieval list and then the neighborhood pool, then you go back to the first stage retrieval list, and then you come back to the neighborhood pool and so on, right? So now you're ensuring that you're no longer limited by the recall of your first stage retrieval. You're also looking at these neighbors, right, who might be friends of potentially relevant guys. And this way, there is a chance of like improving your recall, right? And now once these documents are ranked, probably you can feed them to the LLM. But this still doesn't ensure that the documents which help answer the questions are appear in top 5 or top 10, right? There is no guarantee through this, because all we have considered now is just lexical or semantic relevance to the query and the documents, right? We are in no way are these indicators of whether the document would help answer the question, because a document could be very close to a query because it has some common terms, but it might not help with any form of reasoning required to answer that question. So to capture this, we capture LLM feedback, right? And of course, we can't get Oracle feedback, right? Which is going to say whether the current answer generated by the LLM is wrong. There is no way to know this. So we sort of come up with a measure called semantic uncertainty, right? And we want this to work for both black box and LLMs, which sort of give exposure to their logits. We want this to work for both of these models. So what we do is for each sub question, when we are sort of re-ranking a batch, we send this batch through the LLM and ask it to generate multiple answers, right? So we ask it to generate 10 or 20 answers for this particular sub-question. And now we cluster the answers. So how we do the clustering is through semantic equivalence, right? We use a natural language inference model. So NLI task is pretty simple, right? Given given a pair of texts, it sort of tells you whether one entails the other, right? And you sort of do this for both the texts in both the directions. You get bidirectional entailment, right? Whether both of the texts entail each other. And if this is the case, this is a stronger criterion for semantic equivalence more than cosine similarity between representations, right? And we sort of do this for all pairs of generated answers for the current sub-question, right? For the given set of evidence documents. And we construct what we call as semantic sets, right? So once you cluster, so why we need to sort of do the semantic equivalence or not just direct comparison is because answers could have different terms, but could mean the same thing, right? That's why we check for semantic equivalence. And once we construct the sets, we count the number of sets, right? So the intuition here is like if there is a lot of semantic sets, the LLM is really uncertain, right? And if there are less number of semantic sets, maybe the LLM is more certain. But of course, the LLM could also be more certain about a wrong answer. Yes, that's a possibility. But here we are just trying to measure LLM uncertainty, right? Given a set of evidences. So now we penalize the ranker scores for this batch of evidences by dividing it by number of semantic sets. So more the number of semantic sets, these documents are going to get downweighted, right? If they are making the LLM more uncertain. But rather if the number of semantic sets are low, then those evidences might get scored higher, right? So this is like a proxy for saying whether a given set of evidences will help answer a question, right? And now we do this like for all batch of documents for a given sub-question, and we do this for all sub-questions till we arrive at the answer, right? And we sort of evaluate this on Wiki multi-hop on music QA. If you sort of remember, I presented these two plots, right, with ideal and current state of the art. And this is sort of the end task performance. So we saw huge gains in retrieval, of course. The recall improved because we were moving beyond the first stage retrieval. But we also wanted to see whether this translates to reasoning gains, right? So we evaluated the end task performance of complex question answering on Wiki multi-hop and music QA. And as you can see here, we have this particular idealized upper bound, right? Which is when you give a LLM all the relevant documents, what is the maximum performance you can attain, right? And as you can see on Wiki multi-hop QA, our approach Sonar is pretty sort of tries to approach this idealized upper bound, and it gives like a 10 to 12 point gain over existing state of the art, right? And all these state of the art systems sort of use this classical telescoping pipelines, right? And we see similar gains on music QA. Music QA is a much difficult and complex data sets, but we still see relative gains compared to state of the art. Of course, we have not solved it completely, right? There is still a considerable gap to the idealized upper bound. But we sort of saw that we were able to bridge this retrieval gap and to some extent reasoning gap, right? Which we discussed earlier. And I'm also not going to bore you by explaining all the results in this table, but one thing I wanted to point out is for the table on the right, you can sort of see that this method is more of a framework, right? It translates well across different LLMs. It's not limited to any particular LLM. And this is an example of test time reasoning or test time scaling, right? You don't have to train any models, right? And even this corpus graph is computed offline and does not require any training, right? And so this is all training free, and it sort of gives you performance improvements for free to some extent. And we also did a detailed qualitative analysis, some examples of which are shown in this slide. And we found that it was able to tackle hallucination and knowledge gaps to some extent, right? Of course, it doesn't solve it completely. But one really nice example you see in this table is the second example, right? Which is about who is the screenwriter for a certain movie, who also played in some other movie, right? And what role did he play? So it's a complex question. You first have to figure out who was the screenwriter for Good Will Hunting, and you have to figure out whether he played in Dazed and Confused and what character he played. So if you see self-ask, which is like one of the state-of-the-art methods, it gets the answer to the first question right, which is about who was the screenwriter for Good Will Hunting. One of the answers is Matt Damon, right? But because of this recall boundedness problem, the retriever sort of gives another document about Damon Salvatore, who is a fictional character, right? Not the actor Matt Damon. Because of the lexical match, this gets picked up, and even semantic match ranks this higher because it has no other documents to explore. And in the end, the final answer is wrong, right? Damon Salvatore, which has nothing to do with the original question. But as you can see, Sonar, it sort of gives the most relevant evidences in top 5, which is about the two screenwriters for Good Will Hunting and about Ben Affleck playing a character in Dazed and Confused, right? And these are Wikipedia documents. And we observe that these appear in top 5, top 10, and it gives the correct answer, right? So now I've covered the effectiveness aspect. If you remember, we had this two axes of efficiency and effectiveness, right? So in effectiveness, we sort of tried to close this recall gap and we had some success. But Sonar is not really 100% efficient, right? It's going to add a lot of compute at test time, and probably it might be good for some offline reasoning, like if you want to do financial research or some kind of compositional reasoning. Maybe you start this program in the night and you come back in the morning and you get the outputs to prepare a report, right? Maybe it's good, but it's not really good for end user facing applications, right? It's really expensive. So the next axis we sort of try to solve is this efficiency axis, right? While making sure we preserve this effectiveness, right? And we sort of came up with this framework of online relevance estimation. So if you recall, we had this telescoping view, right? Where we retrieve, we re-rank, and retrieval is really fast and re-ranking is really slow, right? And takes 95% of the time. So what we want to do is cut down this 95% of the time, right? Really bring it down while ensuring we capture this document, right? So if you remember, again, telescoping setting is limited, where you don't capture this really good documents which have low retrieval scores. So um, our goal is to introduce a really inexpensive proxy for the ranking function, right? Which can be learned on the fly by just sampling ranking scores for fewer documents, right? Maybe you don't re-rank 100 documents, maybe you re-rank just 10 documents and learn a really good proxy for this ranking function, right? And for this proxy ranking function to be really good, it has to be really fast too. And for it to be really good while being really fast, it has to capture some features which sort of capture the signals, right? Like documents with low retrieval scores, which are friends of maybe highly relevant documents. Maybe you have to prioritize these documents, right? So if you sort of see this plot, you sort of see a explore exploit dilemma here, right? You could either exploit documents which have already high retrieval scores with respect to the query, or you could also explore documents with low retrieval scores which have potential to become highly relevant documents, right? So this naturally fits into the framework of multi-arm bandits, right? So we take inspiration from linear stochastic bandit literature, and we sort of came up with this very simple framework, right? So assume you have the initial retrieve set, assume you're retrieving like thousands of documents, and it could be any retrieval framework, right? It could be hybrid retrieval where you take lexical scores and semantic scores, merge them and form a retrieval list. Or it could be the neighborhood aware retrieval, which you just saw in Sonar, right? Where you also get this neighborhood guys and so on. So it could be any initial retrieval list. Now what I do is I sort of want to rank this retrieve list in batches, right? So if it's like 100 documents, it's going to be 7 batches, right? If the batch size is 16. So let's say I'm telling, hey, I just want to rank 2 batches, not more than that, to cut down the time spent on ranking. So when I'm ranking these two batches, I call this expensive ranker, get the actual scores for these documents. And I sort of learn this weights of the scoring function, right? Using this actual scores for these documents. And this proxy for the ranker, this particular scoring function is just a linear function, right? Inspired by linear stochastic bandits. It's just a linear combination of different features. And it's linear in weights, right? And these are the weights which you're trying to learn. So you just sample the actual ranker score for some documents, and you also just fit the parameters of the scoring function when you sample these scores. And for the remainder batches, you just use the scoring function, right? You just estimate the relevance using the scoring function, which is like really fast, right? And it's like of order of magnitude, maybe 2x to 7x faster than the actual ranker. And the challenge here is to make sure that the scoring function acts as a good proxy for the ranker, right? It shouldn't have really wrong relevance estimates, then there is no point in efficiency gains if you have a huge drop in effectiveness. So the features are really important. Of course, you can learn the weights, but if you don't have good features, which is capturing the intuition or the necessary signals for ranking, learning this proxy function is no good. So we have this features listed, but of course you could also come up with more features, but the intuition is just based on this taxonomy which we devised, right? Which is query to document affinity and document to document affinity. So query to document affinity is basically your first stage retrieval, right? Which captures whether a document is closer to the query. And you can use lexical retrievers like BM25 or dense retrievers like TCT. And document to document affinity is basically whether two documents are close to each other, right? How close they are. And this is what we captured in Sonar, right? Through the corpus graph. And you could do this again using lexical or dense models like BM25 and TCT. Or you could also repurpose classical IR methods like RM3, right? Where you take the initial query, you retrieve a bunch of documents, then you take some term from this initial documents, reformulate your query, and then retrieve more documents, right? So in a way, it also captures document-document affinity. Or you could just build a classifier which sort of classifies whether two documents are close together or not, right? Which we call as learned affinity. And most of these features can be computed offline, so they're not very expensive and they do not add to the time when you're actually doing the retrieval and ranking. You can almost get them for free, right? You just have to do the lookup. So we ran experiments on popular web search benchmarks, right? To sort of really see if this is offering any improvements or if our intuition is right. We sort of evaluate this on MS Marco benchmarks, right? On version 2, TechDL 21 and 22, which are the most recent benchmarks. And we observe huge gains in efficiency, right? So on the left, you can see the plot compared to state-of-the-art neighborhood aware retrieval methods like GAR and QAM. ORE, which is online relevance estimation, is like 2x to 7x faster than these methods. Depending on the ranker, of course, you could employ BERT-based rankers or LLM re-rankers, right? And based on how expensive your ranker is, you get proportional gains, right? And then we really did a breakdown of the components of ORE to just make sure we are not deceiving ourselves, right? Is ORE really fast, or are any of these additional components which we are adding taking up more time? So to do this, we did this breakdown of how much time is spent in ORE for ranking and how much time is taken to fit the parameters of this linear model and how much time is taken for feature lookup, right? So on the right, you see this plot and you see that the components of ORE, which is the feature lookup component, and the linear model learning component, it's like 10x faster than the time taken for ranking, right? So most of the time is spent in ranking, like we saw earlier, 95%. And the ORE component almost adds very negligible time, right, to the inference. And that's why we are really fast. And to sort of test if we are really sample efficient, we, as you can see on the plot to the left, the figure A, we sort of increase the number of samples being used to learn the linear model, right? It's the number of batches being scored. So if you see, this is for like re-ranking 100 documents. So if you see in the x-axis corresponding to 1, it implies we are only scoring one document, right? We're only calling the re-ranker for one document and the rest of the scores are estimated using the learned parameters, right? The learned linear model. And you can see that it's very sample efficient, as even just for one batch, we outperform all the existing methods. And you can see that as we increase the number of batches where we sample the actual ranker scores, the performance increases proportionally, but it's always outperforming the existing state-of-the-art methods, right? And you can also see sort of see this error graph where we see a huge drop in error after you sort of learn this linear model using the ranker scores. After scoring even one batch, you see this huge drop. Then it's a bit stable, and then you again see a drop as you sample more batches, right? And we see that this intuition holds for different retrieval settings, like adaptive retrieval, which is the neighborhood aware retrieval setting, and also hybrid retrieval, which is just merging lexical and semantic retrieval, right? And like I mentioned earlier, we also evaluate on track DL 21 and 22, and we see huge performance gains. And these are also statistically significant, as you can see in this particular table. So now I've talked about how to bridge the retrieval gap, right? Majorly, of course, it also influences the reasoning gap. And I've shown you how you can reconcile both effectiveness and efficiency, right, without sacrificing either of these parameters. Of course, it's not 100% solved, but we see promising directions in Sonar and ORE to achieve this trade-off. And now I would like to move to the reasoning gap, right? So before we sort of go towards frameworks or solutions for bridging the reasoning gap, I would like to actually stress with a motivating example as to what I mean by reasoning gaps. So on the screen, you see this particular claim, which is saying that repealing sales tax, right, in Rhode Island, basically has led to number of results, which is about bringing so many companies and so many jobs and so much $1 billion a year in sales activity, right? And this is a numerical claim. And there is also this illusory truth effect, right? Where if someone is making a statement and they're including numbers, then the propensity to believe that is more than, let's say, any other blanket claim. So numerical claims are much important to verify, right? And also much harder to verify because you have to make sure each numerical component is correct. And here, if you see, this claim has so many parts, right? So you have to first figure out like how many companies were there before the tax, how many jobs were there before the tax, and what was the revenue before this tax was applied, right? And then you have to get these numbers, and then you have to compare with the numbers mentioned in the claim. So if you sort of break down this task, it's like a multi-step process, right? And to automate this, it's also a bit hard because you have to retrieve precise information for each of these questions, and you also have to do precise comparison, right? Just approximating is not going to be really good to verify this claim. And we built a benchmark of numerical claims, which was published in CKIT to test the reasoning capabilities of different models, right? Of LLMs, fine-tuned models, classical NLI models, and so on. And something really that surprised us was like really small models like Tiny T5, right? Which has 1 million parameters, not really tiny, but in the current scale, 1 million parameters is called tiny, right? We found that it outperforms like billion scale models like GPT 3.5 Turbo or any other model, you name it. And basically, of course, the smaller models were like fine-tuned models, right? And they also had some numerical reasoning capability. But it was still surprising. I mean, this fine-tuning cost is not really large compared to the inference using billion scale models, right? It's very negligible. And we found that we were surprised to see this because this is sort of music to ears for a lot of small scale startups or companies, right? They can just deploy the smaller models, especially for automated fact checking companies. And we found that just, prompt engineering a lot doesn't solve this, like manual prompt engineering doesn't help a lot. Of course, there were minor performance differences, but nothing significant. So we sort of had this intuition that, okay, to solve this task, you need multiple skills, right? You need multiple abilities. The abilities being compositional reasoning, sort of knowing that this claim is compositional and breaking it down into simpler facts or simpler sub-questions. And then knowing to also numerical sensing, right? Like numeracy, knowing that what numbers mean in the context they occur, and retrieving relevant evidence corresponding to context, and actually doing the arithmetic, right? Like comparisons, addition or multiplication, and so on. So we sort of need a composition of skills which can't be achieved through simple manual prompt engineering. But one way this can be achieved is by carefully selecting examples, right? So there is this paradigm of in-context learning, which has been found to work really well, where you sort of pick up really good demonstrations, where you show the input, the output, and the reasoning required to arrive at the output from the input. And you just show these to the model, and the model uses this in-context samples to perform reasoning, right? And this can be divided into two different axes, again, static and dynamic, based on whether you select examples dynamically for each test instance, right? For each incoming instance, or you select a small subset of samples from training set and use them for inference for a particular task, right? So these are also called task level exemplars. And you can sort of draw parallels to the subset selection literature in classical machine learning, right? The task level exemplar selection. So our intuition was, right, if we pick task level exemplars which demonstrate this different abilities, maybe the LLM learns to compose them, right? Of course, it's still prompting in some sense, but it's more principled compared to like just manually adjusting your prompts, right? And below you can see one such example where you sort of give an instruction to an LLM, which is like a system instruction, and you have this exam class, right, which is nothing but your input, your output, and the reasoning required to arrive at the output. And the reasoning is what really demonstrates the abilities. It shows that here you have to know how to read the table, right, and how to perform arithmetic reasoning and so on. So now ICL phenomenon is not being really understood, right, completely as to why this happens, why if you just show a few examples, the performance of LLM skyrockets. And if you do it in a more principled way, it's found to work really well, right? But there are some approaches which sort of try to map them to linear models, as in LLMs learn to compose skills in context through a linear model. There have been some works in literature showing this through mechanistic interpretability and other approaches. So again, we draw inspiration from multi-arm bandits literature because to select really good in-context samples from the vast training set, you really need to value each of these in-context samples, right? You need to know, you need to assign them a value based on whether they would help your LLM solve the task or whether they would not. So to do this, you can't, of course, call the LLM for each of these in-context samples, right? It's really expensive. Of course, some methods do this, but it's really expensive. So we want to make sure it's efficient as well as effective in evaluating the exam class, right? So we again turn to linear stochastic bandits literature and also inspired by this work which shows that LLMs compose skills and context. We come up with a linear model of LLM loss for a particular in-context set of in-context samples on validation set. So we take a small validation set and for a batch of in-context samples, right? So instead of giving each in-context sample in isolation, you sort of always give a batch of in-context samples, right, which demonstrates various skills. So we take a batch of in-context samples as an arm, and we use this proxy model to determine the LLM loss for this particular in-context samples, right? And initially, this proxy model is going to be a really bad predictor of LLM loss. So that's why we are going to learn this on the fly, right? So what we do initially is like we take all the in-context samples and cluster them, right, into batches of 5. And we designate each of them as an arm. So if you see the difference compared to ORE, that each document was considered an arm, but here a set of in-context samples is considered an arm. The intuition behind this is that you always feed a batch of in-context samples in one shot to the LLM. And you also want to consider interactions between the in-context samples, right? So now you have these arms. And you don't call the LLM for all of these arms. You just sample the actual LLM loss for some of these arms on a small validation set. And you use this to update the parameters of the sigma, which is the linear model, which I discussed earlier. And once you learn these parameters, you predict the LLM estimation of LLM loss for all the other subsets, right? And then you pick the top 5 or top 10 subsets, which have the low estimated LLM loss, right? And you use them for downstream reasoning. So this is the broad recipe. Now I'll go a bit more in detail. So on this screen, you sort of see this linear model, right? Sigma, which is just like a bunch of weights, alpha I, where alpha I determines the importance of the ith in context sample in that particular arm, right? So it sort of is going to determine the importance. So if an arm even has like 2 good, really good exemplars, but all the other 3 exemplars are bad, this arm is going to be downweighted, right? Because it's going to lead to a higher loss. And now we have EIJ, which is like a feature matrix, right? And this is nothing but the cosine similarity between vector representations of your exemplar, right? In that particular arm, ith exemplar, which is xi, with the validation sample in the small validation subset, right? So you sort of compute the similarities and average it across the dimension of number of validation samples. So for each arm, you have a feature vector of dimension phi, right? Which is equivalent to number of in-context samples in that arm. So this is how the linear model is constructed, and the alpha I are the parameters which you're going to learn, right? Now, how do we learn these parameters? We're going to do it through linear least squares, of course, but you need an error, right? And this error is the approximation error, which is like the difference between your estimated LLM loss and the actual LLM loss, right? For a particular arm. So of course, you can't sample this for all arms. So at any given point, what you do is you maintain two shortlists, right? And one shortlist is the current set of good arms, which is probably like just top 10 arms out of, hundreds of thousands of arms, right? And how do you determine this top 10 arms? It's like top 10 arms which have the lowest estimated LLM loss, right? And this estimated LLM loss always refers to LLM loss predicted by the linear estimator, right? Initially, this estimate is going to be very bad, but as you go on, it's going to get better, right? So you sort of maintain the shortlist UT, the set of good arms. And then you have VT, which is the set of all other arms considered bad currently, right? And now you cannot again sample the LLM loss for all of these arms. So you randomly sample a subset, right, from VT. And this is called negative sampling. It sort of is a contrastive objective, right? Because since initially your estimates are wrong, you can't just exploit all the arms in UT. You also have to do some exploration, right? So we sort of sample some negatives from VT and also reduce their approximation error, because in future they may have potential to be a part of UT, right? So this is similar to like any contrastive loss. We sort of also judge approximation error on this subset of documents. And then we add up all these approximation errors, and we use linear least squares to determine the alpha parameters which would reduce this loss, right? And here, calling the LLM for this subset of samples is equivalent to arm pulls, right? And you're doing this for a very small set of arms. So this is going to be really efficient, right? And this is just an overview of algorithm. So like I mentioned earlier, at each iteration, what you do is like you you reduce this approximation error, which is on line 7, and determine this parameters. And then you re-estimate the value of the arms, right? And once, yeah. Yeah. Okay. Should I continue, or is there a question? Hello.
I guess you can continue.
Okay, great. Yeah. So what we do here is like once we estimate the parameters, we calculate the new utility for the arms, right, using the linear model. And then we determine the arm which has the lowest loss in VT. If you remember the subset we sampled, right, the negative subset. And then we also determine the arm with the highest estimated LLM loss from UT, right? And you swap these out, because this arm is estimated to have a higher loss and it should be no longer in UT, right? And you do this for each iteration for a fixed number of iterations, right? Or if your approximation error is not changing a lot between iterations, you sort of continue this. And if it's not changing a lot between iterations, it means it has converged, right? And then you stop and you just output UT as the set of good in context samples, subset of in context samples which one might want to explore. So we employ this paradigm of tune and transfer here, where if you see all this exemplar selection happens offline, right? Because it's task level exemplar selection, you do this once, and you can use this subset of exemplars for inference on any test instance for this task, right? So we use smaller LLMs like Llama and Mistral to sort of select this subset of exemplars. And then we can do inference on any large LLM according to the choice of the user, right? So this is similar to MUPI, where people tune hyperparameters for a smaller model and transfer it to a larger model to reduce computational costs. So one thing we observe is that selecting task level exemplars is very robust, because dynamic exemplars vary according to each test instance, and there is a lot of variation, right? There's a lot of variance in performance. But we observe that task level exemplars reduce variance and also enable attributability, right? Like if you got a particular test instance wrong, you can just look at this exemplars and figure out why the LLM would have arrived at a certain reasoning for a given test instance. And the most important part, one of the most important research goals, which was also attained, is that reducing the computational cost, right? So Explorer is very sample efficient, again, since it's inspired by linear stochastic bandits. So we can see that the number of LLM calls made by Explorer when compared to Lens, which is also a static exemplar selection approach, is like really low. So it makes only like 11% of the calls made by Lens, right? It reduces the number of LLM calls by 89%. And we also observed that tune and transfer works really well. You can use any small model as base model, and you select the exam class and it transfers well to larger models. So now I'll conclude with a quick recap. So efficiency and effectiveness, both of these axes is important for robust React pipelines. I think that's two important considerations always to keep in mind when you're working in this area. And classical retrieve re-rank pipelines, which I'd like to call telescoping systems, suffer from retrieval limitations, and they also impact reasoning, right? And even if you give the perfect evidence, LLMs are still limited in reasoning. If you based on what's the definition of reasoning. But even like on most simple reasoning tasks, LLMs are still not mastered these tasks. But one way to maybe sort of overcome this gap is to have a really good retrieval and also doing careful selection of this exemplars, right? So that maybe LLMs compose these skills in context. They're really good at composing skills when demonstrated what these skills exactly are. And test time reasoning is actually picking up a lot. So end-to-end test time reasoning has huge scope. Right now, test time scaling is more focused on different decoding strategies for LLMs. If you see a lot of test time scaling works in the most recent times, like DeepSeek or O1 or O3. But sort of figuring out how to do this end-to-end for retrieval and reasoning, and by incorporating LLM uncertainty as feedback, I think this is a ripe research area. And most importantly, how do we do this in a scalable manner, right? If you see O1 or O3, for some even simple questions, it's saying like, I'm going to sort of think for like 2-3 minutes. And for some applications, this is not really acceptable, right? So this concludes my talk, and yeah, I'm open to any questions.
Thank you, Dr. Venktesh, for the very informative talk. I request audience to ask your questions, if any. Okay, I hope there are no questions. So I would like to end the meeting. Thank you everyone for attending. Thank you again for the talk.
Thanks a lot.